Okay, good afternoon, everyone. For this GTP seminar, we're very happy to have Cihan from Bilkent University in Turkey, who is going to tell us about simplicial distributions and contextuality. Cihan, please.
Hey, thank you very much for the invitation. It's a pleasure to join on Zoom. Yes, so I'll be talking about simplicial distributions. So these are new objects that we have started to work on, and the main motivation is coming from contextuality. So this is a notion that is a feature of a collection of probability distributions, and it manifests itself in the measurement statistics of quantum systems. So this is something physical. So I'll be using a lot of algebraic topology, mainly simplicial sets. So I'm assuming most of the people in the audience are familiar. But okay, so I'll try to be not too technical. If you have any questions, you can just ask. So contextuality, as I said, is a feature of collections of probability distributions. And on the left-hand side, so I'm mainly motivated by these two approaches, sheaf theory and chain complexes. So the collection of probability distributions you should actually more formally think of as a sheaf of distributions. So I'm not going to be defining them very precisely. I will tell you how simplicial distributions are defined formally, and then how it makes connections to these two approaches. So mainly, so the boxes here on the left-hand side. So here, this box, for example, represents the distributions over a distribution on the set of 2 bits. So 0, 0, 0, 1, 1, 0, 1, 1. So the numbers inside the boxes, they're greater than or equal to 0, and they sum up to 1. And we can actually marginalize in 2 ways in these boxes. And this represents now a distribution on bits 0 and 1. When you consider more than one big boxes, you would like to match over these smaller boxes. So that's kind of like a sheaf structure. And in the sheaf theory, you can talk about global sections, and very briefly, you can talk about contextuality in this sense when there is no global section. So that's kind of like a very precise definition in sheaf theory. You can formalize these things. And this is written by computer scientists, essentially, Samson Abramsky and Brandenburger. So that's the paper at the bottom. So this is the main paper I'm referring to. So it actually captures a lot of different ways contextuality appears in physics and formalizes in a nice way. So simplicial distributions is going to go beyond this. So it will encapsulate both approaches. And on the right-hand side, so this is more quantum mechanical. So this is essentially something we developed more recently together with Robert Rosendorf, Sam Roberts, and Stephen Bartlett. And the motivation was more quantum mechanical. So that's why you see these operators. So here, X is the Pauli operator, 2x2 Pauli operator, and 1 is the identity. And physicists usually take these tensor products of operators just to create convenient sets of operators that actually pairwise commute. So in this approach, you come up with a space where the edges of the space are labeled by these matrices. And the property here that you seek for is that when you have these, the edges on the boundary of a triangle, they're supposed to commute, the operators. And they sum, the product of these operators are identity. So that's kind of, if you know about classifying spaces, it just, resembles a lot of the structure of a classifying space. And here, instead of, on the left-hand side, there's this global section. On the right-hand side, there are cohomology classes that can detect contextuality. So within the framework of chain complexes. And that's the paper. So yeah, so this is like a very rough introduction to like two approaches that has been present to the date when the simplicial distributions has been introduced. So the main innovation here is to jump from discrete sets of measurements and outcomes, just think of a physical system. You have a discrete set of measurements and discrete set of outcomes. To a
Excuse me, can I
space of
ask a question
measurements.
before you?
Of course, yes.
Thanks. So contextuality here is it means in general that there's some failure of a local to global principle, right? Is that the idea? And then the context and contextuality is that locality that now matters. Just trying to understand the terminology.
Yes, yeah. So here actually I haven't defined anything. So the closest thing I can talk about here, I think the notion of global section. So when you have these collection of probability distributions, which are matching, meaning that you have this nice local structure, the failure of a global distribution, or it's also called a joint distribution, is called contextuality. So that's the definition within the sheaf theoretic framework. But I will define contextuality in a much simpler way using simplicial sets. So then I can actually connect back. Yes, I haven't provided any definitions. So I just want to tell sheaf theory and chain complexes have been used up to this point, and then simplicial sets are quite natural. In subsuming these two approaches. So essentially, the talk is going to be about simplicial sets. And simplicial sets in this talk are going to be modeling spaces. And the main jump here, as I said, going from discrete sets of measurements and outcomes to spaces of measurements and outcomes, where space are modeled by simplicial sets. So these are combinatorial objects that are more general than simplicial complexes. So you can do more gluing and collapsing. And this approach is going to subsume sheaf theory and the chain complex approach to contextuality. And the main reference here is this paper. So most of the stuff will be from this paper, joint work with my postdocs Aziz Karuf and Selma Ipek. So the first definition I want to provide is what do I mean by a distribution? So I consider this set D of U, where U is a finite set. It doesn't have to be finite, but let's take it to be finite. If you don't consider finite set, then you have to assume finite support. So its distribution is a function into non-negative reals that sum to 1. So this is very basic definition. That's the kind of distribution I have in mind, very elementary. And the important thing here is that if you have a function between two sets, you can push forward a distribution using this simple formula. And usually people call this, in the context of probability theory, marginalization. I think push forward is more natural from a categorical point of view. So you essentially sum the numbers in the preimage of each point in the target. So more formally, you can think of it as a functor from category of sets to category of sets. Of course, I need to impose finite support if I just take arbitrary sets. But in the talk, everything is going to be a finite, so we are safe. So, for example, the box I just mentioned is representing a distribution on pairs of bits, z mod 2 squared. And if you take the function projecting onto the first coordinate, that will correspond to the following marginalization. So I'm just going to color the boxes, the numbers that I'm summing. So I'm just actually summing these two to get the 0 probability, and these two to get the 1 probability. Of course, I can do projection onto the second coordinate. That would be summing these two numbers to get the 0 probability, and these two numbers to get the 1 probability. So these are the natural directions: projection to the first coordinate, projection to the second coordinate. And there's a third one, in fact, which will be important as well. I can also take the sum of the bits. This is also a function. I can marginalize or push forward along this map too. And that would correspond to, maybe I'll just show it in the other box, summing the diagonal to get the zero probability and the anti-diagonal to get the 1 probability. So these are going to be useful. So just to define what a space is in this talk, it's a simplicial set. It consists of a sequence of sets indexed by natural numbers, and together with 2 kinds of maps, phase maps that lower the index by 1, and the degeneracy maps that increase the index by 1. So of course, these I and J, they're also indexed over certain numbers, and there are a certain number of those. I'm not going to be very specific about those. I think I will give an example where it's more specific. So this is these functions, they satisfy something called the simplicial identities. Of course, there's a more categorical way of describing what a simplicial set is. So you have to define a simplex category, and in that case, a simplicial set would be a contravariant functor to the category of sets. So, but usually for practical purposes, it's easier to think of it as a sequence of sets where these sets are the n simplices. So this is the set of n simplices. And what the phase and the degeneracy maps do, phase maps tell you how to glue the simplices, degeneracies tell you how to collapse them. So this is essentially what the simplicial set contains as information. And the simplicial set map is a sequence of functions for between each set at degree n that are compatible with the phase and the degeneracy map. So here by F sigma, I mean the image of Fn at sigma. So this is an n simplex of y. So I will be using this shorthand notation. With this notation, compatibility with the di means this equation. So the phase of F sigma is f of the phase of sigma, and a similar equation for degeneracies. But in the talk, we will be mostly focusing on phase maps. So that's where the compatibility is encoded by. And the main example of a simplicial set is, essentially the unit of the simplicial sets is you can think of as an n simplex. So here I'm describing a 2 simplex. So the n simplices of a 2 simplex is given by sequence of integers between 0 and 2. All of these numbers. So you're allowing repetition, of course. And the phase maps, the ith phase map omits the ith index on the top, and the jth degeneracy doubles the jth index. From a geometric point of view, what's important is those simplices where there's no repetition. And these are called non-degenerate simplices. So we have this 2 simplex that correspond to the sequence 0, 1, 2. And we have, so X here denotes the sigma 0, 1. This is sigma 1, 2, and this is sigma 0, 2. These are all the non-degenerate simplices. They're the degenerate ones where the indices repeat and they're omitted in the picture. They are collapsed. That's why we don't draw them. And essentially, understanding this example amounts to deriving the simplicial identities. So essentially, this copying, so maybe I should call this deletion, this operation, and then this is the copying. So the deletion and the copying operations, they satisfy certain equations, certain relations, and simplicial relations are essentially those ones. So that's the main example. I will be thinking about triangles a lot in this talk. Now we can talk about distributions on spaces. So if you take a simplicial set Y, then the space of distributions is essentially given by dy, whose n simplices are the distributions on the n simplices of Y. So, I mean, easier way of talking about this would be more categorical. So okay, anyways, I haven't gone into that direction, but let me talk about the face maps and the degeneracies. So how do you obtain the face maps of dy if you want to go from dy n to n minus 1? So I can use the face map of y, which takes me from yn to yn minus 1, and apply the push forward using this d of di. So I can push forward the distribution along di. Similarly, I can push forward the distribution along degeneracy, and the resulting object is another simplicial set. Okay, so that's the distribution on a space. The main example we will consider is going to be the simplicial set, which is the nerve of Z mod 2. So Z mod 2 is an additive group with two elements. So the two simplices in this simplicial set, I mean, maybe I should write the n simplices more generally. So the n simplices are given by n bits. And you have the face and the degeneracies essentially defined using the group operation for the face maps and using the identity for the degeneracies. So I'm not planning to write down the precise formulas for the degeneracies and the face maps. I want to just write down the face map for the two simplices. So if I want to write down the ith face map for a pair of bits, so a pair of bits here, AB could be 0, 0, 0, 1, 1, 0, 1, 1. So I have four two simplices as in the picture. And the face maps, there are three of them for 0, 1, and 2. The first one omits the first entry, so this is just B. The second one sums the entries, and the last one omits the last entry, so this is A. So we can see this on the triangle. So the zeroth face is this one across 0. The second face is this one across 2, and the first face is 0 plus 0, which is 0. So I can just complete the D1 here. So this is just a binary mod 2 sum of these entries, the two sides. So on this example, we will be talking about distributions. So distributions on the nerve. Again, I'm interested in the two simplices, as you will see why. So let me remind you what the two simplices of this would be, or let me remind you the n simplices. So this would be distributions on Z mod 2 n. For two simplices, this distributions on pairs of bits. So we have essentially four numbers, and these four numbers are placed in the triangle in this way. And for the one simplices, we have just a distributions on the bits, so P0 and P1. But since the sum of these two numbers is equal to 1, I'm not going to be writing down P1. So P0 suffices. So now the face maps, if you unravel this definition right here and push forward the distribution, as we have seen in the first example of pushing forward along a map, so this would correspond to summing along the following. So if I sum these two numbers, I get the P0 at X. If I sum these two, I get P0 at Y, and I can sum these two, the third direction, to get the Z edge. So usually we denote the Z edge by XOR of the X and the Y label. So XOR here means like a classical logic gate. The reason is that to get 0, you're summing 0, 0 and the 1, 1 probabilities. So that's why we can think of it operationally as an XOR, or you can just take it as a notation. Either way is fine. So this is the fundamental object essentially in this talk. These four numbers with these three sum to the edges. Any questions so far?
Yeah, could I ask? Can you hear me?
Sure, yeah, I can.